Okay. So let's begin with a word of prayer. Heavenly Father, we thank you for this afternoon. Again, Lord, I thank you for these students for the first week just being done. Just pray you be with us today. Help us to glorify you again, Lord, in what we do. Just pray that students who have good questions as they think of them. And just pray we can make the most of this time, Lord, for your glory. In your name I pray, Lord Jesus. Amen. All right, guys. So what questions you got for me? Oh, somebody else returned the book, huh? Don't like the 8th edition, eh? I do think it stops being so unsynced up a little bit later in the course, but it is, like I told you, a kind of a nuisance. So, all right. So what was the question? Yep.
All right. We're looking over the homework problems, right?
Uh-huh.
Number 8 here.
Now, when you say number 8, what do you mean by that?
Mission problem. So the one you wrote out.
Uh-huh.
It gives us two vectors, and we're supposed to find the vector of length 1 that's perpendicular to both of them. So I did that using the cross product and scaling it down. And then the second part, we're supposed to find three values, three constants.
So here's let me just talk about the problem. Let me put the problem up here so we're all on the same page. So you got these two vectors, and you're supposed to find a vector c, length 1. So I could write c without the vector equal to 1 to communicate that, which is orthogonal to A and B, right? And you're fine with that part, right? And then you're supposed to find C1, C2, C3, for which, let's see here, 3, 4, 5 is equal to C1A plus C3C. Now, I will admit that the grader has like a little bit of work to do here because there are two possible answers. So what was the
conundrum was that perhaps I made a mistake, but the perpendicular, the
orthogonal? Yeah.
orthogonal line, the vector, its x and y coordinates were equal, just like vector A and vector B. And then I was trying to figure out how, you're using three constants down below, you could have
Well,
the x components add up to 3 and the y components add up.
Well, let me give you a hint on how to find C1, C2, and C3. All right, so how about this? What if I had 3, 4, 5 is equal to, say, C1 times 1, 0, 1 plus C2 times 1, 0, minus 1 plus C3 times 0, 1, 0. How would I find C1, C2, and C3? What sneaky thing can I do? So I made up these vectors that I just wrote down here with a specific structure in mind. And in fact, so this is like A, right? And this is kind of like B. So I constructed A and B so that A dot B is 0. And in fact, I think if you look at these, you might also notice that A dot B is what? Yeah, it's 4 minus 4. It's 0. So this hint I'm giving you is not at all disconnected from the problem that you're given. So here's the cool thing: if you have, and by the way, this is, this is plus or minus A cross B. Well, it may be some multiple of K. It's some constant times A cross B, because it's perpendicular to the other two. So by process of geometric elimination, if it's perpendicular to both A and B, it must be collinear with the cross product of A and B. Okay, how do you find C1, C2, C3, right? How about this? If I take 3, 4, 5, and I take the dot product with A, what does that give me? What happens to this piece and that piece? I'll write it out symbolically, okay? Right. Yeah, these pieces are 0. Because A cross B is so constructed as to be perpendicular to A, right? So the dot product with A is 0. Aha! So what we really have then is C1. See, C1 is just equal to 3, 4, 5, dotted with A, which was what? Dotted with 1, 0, 1, in my made-up example, divided by A dot A, which is what? Well, I'll write it as A dot A. But in this case, A dot A is just 2, right? So, in fact, C1 is equal to 3 plus 5, 8, 8 over 2, 4. How would you find C2? Take the dot product with B. That will give you an equation for C2, which you can easily solve. And to find C3, you take the dot product with A cross B. Oh, you take the dot product with 0, 1, 0. Of course, I know what that is. Okay, this is y hat. If I take a vector dot y hat, it picks off the y component. So I already know that C3 is going to be 4 by inspection. So the idea of this problem is just like a slight generalization of the idea we went over in class, which is that if you have A, equal to AX, AY, AZ, since I haven't used that notation yet, I figure I'll use it now. Okay. Then A dot X hat will be AX, and A dot Y hat will be AY, and A dot Z hat will be AZ. So you can pick off components by using dot products. And you're like, well, how is that the same as this? Well, remember, this is just another way of writing. So I've got a sum of these 3 vectors. If I want to pick off what these coefficients are, I can take dot products. Now, this only works if the 3 vectors you're using are in fact orthogonal, right? And in this case, the dot product didn't directly give me C1 either, right? I had to divide by this. Right. In the case of x hat, y hat, z hat, you don't have to divide by anything because the length of those vectors is 1. They're unit vectors, so they directly select the component. Is that? I think you can figure it out.
I'll show you afterward what I ran across, but I probably made a notation error. But that does make sense.
But yeah, that's a path through this problem. Next question. You can also ask me about the questions in the book. That's also fine. But if you do that, give me kind of, or you can ask a conceptual question, whatever you want.
With your notation, when do you use the angle brackets and when do you use the parentheses?
When do I use angle brackets? When do I use parentheses? It's not, yes. So if I use angle brackets, what I mean to emphasize is that it's a vector. If I write, parentheses, I mean to emphasize that it's a point, but you can use either one. It kind of depends on whether you're thinking of it as a point or as a vector. And we interchange between the two, right?
Right.
So, I can envision a more careful calculus 3 where we made a systematic demarcation between these two things, and I punished students for not using the right object in the right way. But I don't want to do that. So, fight. Oh, okay. Yes?
I was just wondering if that was similar to the R naught that we were using a couple days ago, like having a vector be a specific point.
Right. Yeah. Yeah. Exactly. So that's a good observation. R naught we thought of as a vector from the origin. But I'm also thinking of it as a point on the plane or the line or whatever. It's the base point. So there's a good example of where I'm abusing this identification or using it, depending on your viewpoint. Yeah?
Probably no question, but I don't understand how you got a dot a equals 2, because I thought that you...
I changed the rules of the game. I'm talking about this a. You are well justified in not knowing where a dot a. Now this a dot a would be like 4 plus 4 plus 1 would be 9. Yeah. So that guy has length 3, I think. Oh yes.
I'm still confused how you got A cross product of B from 0 and 0.
Oh, I just know it has to be because it's perpendicular to both of those. If it's perpendicular, it has to be collinear to the cross product, but we can calculate it. It'll take me like 3 seconds. So this is a great one to use, instead of using the determinant formula, to use algebra. So it's actually a great question that you just asked because it gives me an excuse to do this. X hat plus z hat crossed with x hat minus z hat, right? That's A cross B. So one way we can calculate cross products, it's not usually a very efficient manner, but it is here, is just to multiply out, distributing with the properties of the cross product. What's x hat cross x hat? X hat cross x hat is, it's not x hat squared, no. It's 0. Any vector cross itself is 0. We proved that the other day, right? So x hat cross x hat is 0. Z hat cross z hat is 0. I don't even need to write those down. The only thing that's non-trivial here is x hat cross minus z hat, right? Plus z hat cross x hat. But if you switch the order and use the minus, this just gives me 2 z hat cross x hat. Which, by the way, is 2 y hat. Or if you like, 2 times 0, 1, 0. So apparently k was 2. I knew this without calculating, though, because I know by process of elimination, if a vector is perpendicular to both a and b, it must be collinear with a cross b. It's got nowhere else to go in 3 dimensions. Now, if we were in 4 dimensions, it would be another story. We wouldn't have a cross product. We have to think harder. Yeah.
I have a question from the mission, problem 2b.
Uh-huh.
That you can find from a point to the x-axis.
Mission 2b, problem 2, part B, find the distance from a point to the x-axis. Is that right?
I don't know, it has its own coordinates.
Well, remember, the x-axis is an extended object, right?
Right.
So we said the other day that we're going to agree that if we take a point, say ABC, then the distance from that point to some extended object is the smallest distance.
Small.
Right.
So to the origin.
Well, I don't know. Let's see here. Maybe not. I mean, depends on, my picture is making trouble for me. Let me put it over here. So there are 2 lines. You can think about the origin, right? That's true. That would be one place where the x-axis is going. And so there you'd have the square root of a squared plus b squared plus c squared as your distance. But I really think that distance, let me see here if I can draw it like this. If this is my y, if this is my z, if you can envision the x-axis coming out of the board, that might be helpful. So imagine the x-axis just coming out of the board, right? And then envision the point as being this, right? I think it's clear the shortest distance to the x-axis should be this one, right?
So that would be the origin.
No.
That wouldn't be the origin.
No. The origin has this extra bit right here. Unnecessary. Well, another way to look at it is it should be, if you can think about putting this point in a plane, the plane, oh goodness gracious. I need another picture, so
Dr. Cook, if I may, there's a simple way to think about it. Just think about an actual three-dimensional space like a box. Put a dot in the middle of the box. It's quicker to go to one edge of the box than to the corner of the box.
Okay.
Mhm.
So, I was just having trouble visualizing that.
yeah, well, I'm having trouble drawing it. But no, it's not the origin. It's going to be the point on the. It's the point on the x-axis that has the same
Same
x-coordinate.
You can calculate it actually just using B and C.
Right. So like this point should be what? It should be a 0, 0. If I say much more, I'm going to tell you the answer. Yeah, yeah.
Can A be anything? Can we do it anything on the x-axis? No.
We're saying what point on the x-axis is closest to the point ABC? It's the point A, comma 0, comma 0.
Okay,
If if A is negative, it's going to be where I have a hard time drawing. If A is positive, it's kind of what it looks like. Part 2A wasn't too bad, right? The distance to the other point, like that. We're good on that one. How about the line? Do you guys understand how to do the line question yet? No. All right, so let's think about that. How do we find the point closest to a line? Let me just work another problem. It's important that you have a chance to. I don't want to just work the problem in the mission. If I do that, then it kind of defeats the purpose. Let's see here. Let's talk about this line parameterized by r of t equals to 1 plus 2t, 3 minus t, and 4 plus t. There we go. That's a line. And let's see here. Base point what? 1, 3, 4, right? And the direction vector is what? I can see 2, minus 1, 1 from looking at the formula. All right. Now, the question we wanted to ask was, pick a point off the line and then ask what point on the line is closest to that point, right? So, you guys give me a point, any point. Odds are against the point you randomly pick as being on the line, so don't try to thwart me in my purposes. What? 371. Like, how do you know the point's there? I don't. This is just a picture to guide our thinking, right? It's almost, well, there comes a point when drawing pictures which are representative of the objects carefully becomes important, but not here. Well, maybe. We'll find out soon. Is that on the line? Sorry, I just don't trust you. Let's see here. If you put 3, that means t is equal to what? T is equal to 1 to get x equals to 3. If t is equal to 1, that means y is equal to 2. Good, it's not on the line. Okay. So geometrically, we know what we want to do. We want to find this perpendicular bisector to the line, right? And we want to find this point. This is the point we're interested in. Where is this, right?
Does bisector really have any meaning there, or?
Sure.
What's it bisecting?
Well, if you study the planar geometry in the plane which is formed by the line and the point, you have a plane and its usual meaning of bisector, yeah.
How do you from a point and not from like the equation? What is from the equation? Like if we don't have the base plan effect, we just have point equals 1. So is it like the same concept, or?
Well, I give you 2 points on the line, so you can find the equation of the line from those 2 points. I'm solving a related but different problem. Yeah, fair enough. So if you want to get to get from what you're given to this, if you want to just bootstrap the example I'm doing for you right now, you would find the parameterization for the line and go from where I'm starting. But if you see the idea of what I'm about to do, you might be able to just go directly with that information. Let's see. So where is this? How do you guys find that? So here's what I do. I just find another point on the line. Oh, how about the base point, right? We have that one. Where was it? 1, 3, 4. And so I can find this vector. Let me call it A because I have not so much imagination. What is that? That should be, take the difference of 3, 7, 1 with 1, 3, 4. What's that give us? 2, 4, -3. Okay. Now here's where we use the projection. To get this vector down here, that's going to give, I'm going to get that from the projection onto the direction vector of the line of A. Now, what was that? Well, V, what's the unit vector in the V direction? It's 1 over V, right? So the direction vector V hat is 1 over the square root of what? 4 plus 1, the square root of 6. 2 minus 1, 1. And so what I have is I've got A dot V hat, that's the formula for the projection. That gives me the shadow of the A vector into the V direction. All right? And so what is that? I have 2 square root of 6s, so it just gives me a 6, right? Can you take the dot product? What we got? 4 minus 4 is 0, minus 3 over 6, 2 minus 1, 1. What do we get? Mm-hmm. I'll take that. Now, can you see how that allows you to get the point that we're after? How do we get the point? Let me give the point a name. We'll call it Herbert. Okay, so what's the formula for Herbert then? Can you see it geometrically? We can start here at 1, 3, 4. Right? And then we add what? This displacement. That gets me where I want to go. So apparently the closest point is 0, 7 halves. 7 halves? Huh, funny.
That doesn't happen every day.
Now let's go back to the problem that's in the mission and see if we can solve it without the, what did we really do with the parameterization here? Not much. All I did was I used it to get a direction vector and a base point. So you're given those 2 points, right? Let's call them P and Q. And you're given another point off the line R. So all you really got to do is look at this vector, A is equal to, PR, and find what? So if this V is equal to what? PQ. And so here's the line. Yeah, and again, you just use the projection to get this right here. That's not the answer. We have to, P plus that gets me to the point I'm interested in. So. Next. Sorry.
13.1.17 from the text.
You are, of course, allowed to ask additional questions if something didn't make sense, okay? But what's up?
Text question, 13.1.17.
13.117, may I steal someone's book? For example, you. Don't worry, I'll give it back. Number 17, huh? We're looking at a sphere, and we're supposed to figure out what sphere is it. So we've got x squared plus y squared plus z squared plus 4x minus 8y minus 2z plus 5 equals to 0. And we're supposed to show that this equation represents a sphere and find its center and radius. Now, I have not talked about the equation of a sphere yet in here, so let's get that out of our... What is a sphere? It's the set of all points that have the same distance from some central point. How do we write that as a vector equation? How about this? Here's your center point. Let's call it C. And here's a point on the sphere. Let's use R. Then what's all points on the sphere? What do they look? What's the thing that makes them on the sphere? Is they're equidistant from that center point C, right? So if you look at the radial vector that connects the center point to a point on the sphere, this guy, right, which is what? That's R minus C. What do we have to have? We have to have the length of R minus C is equal to what? A constant, right? And we'll call that constant big R. That's the radius of the sphere. Here's the vector equation of a sphere. Now, if you flesh this out in terms of dot products, if you look at, okay, suppose I have x, y, z minus x naught, y naught, z naught, and square that, that's equal to r squared. Out pops x minus x naught squared plus y minus y naught squared plus z minus z naught squared equals to r squared. There's the Cartesian equation of a sphere with center x naught, y naught, z naught with radius r. So just like a circle, just add one more thing, right? Of course, I could have jumped straight to that from the distance formula discussion we had before, right? But so what we got to do is to complete the square, that's all. It's just a completing the square question. So essentially all you want to do is look at where are your x's, right? You got x squared, what else do you got in x? 4x, right? So I take x squared, I take 4x, I rewrite that as x plus 2 quantity squared. And since I just added 4, I have to subtract 4. If you don't understand what I'm doing, you don't understand completing the square, which is entirely likely. Let's see here. Plus y minus 4. But don't fear, it's really not much what I'm doing. All I'm doing is I'm just grouping the stuff with y together and rewriting it as a square, but when I do that, I end up adding a constant. What constant do I add there? If you square it, you get 16. That 16 was not in the expression before, so to be fair, I have to subtract it. So minus 16. So the thing I underlined, the thing in red is exactly equal to the terms I'm underlining in red up here. The thing I wrote in purple is actually equal to the thing I underlined in purple in the upper line. The thing I'm about to underline in green, if I have it. No! Someone from the box. Ah! It's close. This guy, that gives me plus what? Z minus 1 quantity squared, but I added 1, so I have to subtract 1. And then you still got that 5 sitting there minding its own business. And then we just reorder everything. X plus 2 quantity squared plus y minus 4 quantity squared plus z minus 1 quantity squared equals to what? What you got here? You got 20, 21, 21 minus 5, 16, 4 squared. Aha. So it's at minus 2, 4, 1, radius 4. Probably the main obstacle most of you had for that problem was maybe you never were quite taught completing the square. Maybe it was never quite expected of you. That might have happened in your previous mathematical life. I don't know. Next question, or any question about what I just did there? Yes, sir. Mm-hmm. 13.3, number 13. Okay. Thanks. Much appreciated. Number 13? 13.3, number 13. No. Oh, is this a notation problem? We have 3i plus 4j. See, the book is, for some reason, won't get with the picture. That's 3x hat plus 4y hat. Okay. And you're supposed to find the norm of the vector? Oh, that's 13.2. Leave him alone. He's helping me out. 13.3, number 13. Okay, that one was easier. Okay, so I can't. If that's A, this is what? 5. Okay, done. Sorry, while I'm at it. Make the most of it. 13.3, number 3. Number 13. Number 13, okay. 3 was pretty easy, wasn't it? Let's see here. Find the unit vector, direction angles. Okay. So that begs the question, what on earth are direction angles, right? What do you think that means? Well, it's pi over 3, pi over 4, 2 pi over 3. Okay, thank you, sir.
What I would guess is that they're using each axis as sort of like a polar coordinate plane.
Kind of like that, but not a polar coordinate. It's not really a, it's, okay, so the standard angle is based on taking the vector, projecting it down to the xy plane and sweeping over. These angles are not like that. So the definition, if you will, so if this is A, then the direction angles, I believe, I'm about 95%. If somebody here is otherwise inclined, tell me. But I'm pretty sure this is what he calls alpha, this is what we'll call beta, and this guy is what we call gamma. These are also called Euler's angles. And so the definition of alpha would be this: A dot x hat is equal to A cosine alpha. A dot y hat, A cosine beta. A dot z hat, A cosine gamma. So you can write a vector in terms of its direction angles as follows. It's A times cos alpha, cos beta, cos gamma. It's kind of like the cosine theta, sine theta thing we found for the plane, but you need 3 angles in 3 dimensions. Now, I've asked a token question about this in the homework, so you guys have seen it. I don't typically use this much for anything else, but it is a classical notion that you'll find in like old engineering books, maybe new engineering books. So it's worth seeing. That's why there's a homework problem on it. But that's the definition. The angles with respect to in your homework somewhere, I've asked you to find the angle of a vector with respect to an axis. That's a direction angle. So I use the dot product to find the angle, right? Because this gives me, why isn't there something else? Isn't it A dot B cosine theta? Where's the B? Well, x hat's a unit vector. So there's no, it's just the A cosine. So I suppose you just go, for this problem, you just go 1 cosine pi over 3, 1 cosine pi over 4, 1 cosine 2 pi over 3. So that's what? That's half 1 over the square root of 2 And thing I don't know off the top of my head. Shame from negative 1/2. Yeah, I think I'll take that. Negative 1/2 sounds right, because then that gives me a equals to 1/2, 1 over square root of 2 minus 1/2. And I could put a hat on that because it's got length 1, right? 1/4 plus 1/2 plus 1/4, otherwise known as 1. I can calculate the length of its 1. So up to a sign, he has to be correct. But it's cosine of 2 pi over 3. That's a little bit bigger than pi over 2. Cosine looks like what? So it's got to be negative, yeah. Indeed. Thank you. Yes, sir.
I have some questions about defining some words here. So problem 12 says find the standard angle. What is the standard angle? And then the bonus problem.
The standard, first of all, the standard angle is the polar angle.
Okay.
As you know, in quadrant 1, it's between 0 and 90 degrees, quadrant 2, 90 to 180, quadrant 3, 180 to 270, and so forth.
Okay.
Yeah.
And then bonus, prove blah, 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 using index calculation. What is index calculation?
What is index calculation? It's basically these formulas. So to this one, you've got A cross B cross C, right? So like basically what you do there is you say, okay, well that's the sum over I and J of AI B cross C J epsilon I J K X hat K. And then you just keep breaking it down. I mean, eventually you got sum over, let's see here, I J K L M. I think I and L and M will do. That would be epsilon. Well, I'm going to bring the epsilons to the front, so it ends up being epsilon. Oh, fine, I won't. It's AI epsilon L M J BL C M epsilon I J K X hat K. Yep.
What does the epsilon stand for?
It's the completely anti-symmetric symbol. So like epsilon 1, 2, 3 is 1, but then epsilon, if you flip any of the two indices there, you get a minus. So it's 1, 2, 3, 2, 3, 1, and 3, 1, 2 are all plus 1. But then like 3, 2, 1, or anytime you're counting down, you get minus 1. We talked about it in the cross product day. It's a quick notation for the cross product, really. This is a bonus question. It's a shorthand for the cross product in short. Oh, that's what that expression means. But basically, the thing about this, to prove this, you need a little identity. You notice here that the one of these indices is linked. I think it's the J, right? J is matching up, but the L and the M and the I and the K aren't linked. But there's this identity that says that the sum over K of, well, let's say over, well, I need a different letter. We say the sum over L of epsilon I J L epsilon L K M. Well, turns out is equal to the Kronecker delta I K Kronecker delta J M minus Kronecker delta I M Kronecker delta J K. And so if you use this down in here, you end up getting those two terms that they have there. That's a sketch. I mean, the identity in black you use, and then it rips apart the cross product of the cross product into the difference of two dot products multiplying vectors. It's a bonus question, though. Obviously, I don't, expect everybody to do that. You can make an A in this course and not understand an inkling about index calculation. I'm showing it to you for breadth, not for your GPA.
So 13.1.37.
Number 37, 13.1.
Yep.
Do you have a... It seems like it's fallen to you.
13.1. Yep.
We're supposed to describe the solid, huh? Now, some of these problems are a little bit out of place for what we're doing, but they're not the worst thing. I mean, they are inviting you to think more deeply about three-dimensional coordinates, right? So that's a good thing. 37. We've got x squared plus y squared less than or equal to 4. And what else do we have? 0 less than or equal to z less than or equal to 4. So basically these two conditions for x, y, z in T. All right, so T is a set which is built with these two conditions. What are we supposed to do? Just describe it. Okay, so the it's T. That would be one description. That's not the one we're looking for.
Height, radius 2, height 4?
Yes. Yeah, right. So if you envision this, a cylinder is like this. So basically this is z equals to, this is x squared plus y squared is equal to 4. The reason we know it's a cylinder is because it's x squared plus y squared equals to 4 independent of what z is. So if you look at any particular z plane, right, then you look at what it makes on the plane, it's a circle, right? Circle radius 2. And that happens at arbitrary z. So it's circles, it's stacks and stacks of circles, but geometrically you know what that is. That's a cylinder. That's a right circular cylinder, radius 2. Now this part right here, 0 less than z less than 4, it cuts it off. It gives the base z equals to 0, and it gives the cap at z equals to 4, so it doesn't go on and on forever. Right? This is something we'll do integrals over later. We might take an integral of a function over such a thing. So, yeah.
Problem 4 has dimensions. If you're done with that one.
Yeah. There's not much to say about that. Let V be a vector. So you got V is a vector. It makes a 120 degree angle with the what? Positive x-axis. All the direction angle stuff I just erased, it's all for positive axis, by the way. So that actually would be the so-called x direction, the direction angle with respect to the x-axis. I called it alpha. 60 degrees with respect to the what? Positive y-axis. I guess that's what I just called beta, huh? And a 45 degree angle with positive z. In addition, you're given that v dot x hat is equal to minus 10. Find v. So what's the question? I mean, what's your question about the question?
I don't know where to start.
Well, I would think the cosine angle, the direction cosines I just talked about would be helpful, right? Because, I mean, we just went over if v, we can write v as equal to v dot x hat, right? Plus v dot y hat plus v dot z hat. And so this is what? This is v cosine alpha x hat, v cosine beta y hat, plus v cosine gamma z hat. But by the way, this is alpha, this is beta, this is gamma. So the only thing you're missing then is the magnitude. And that you can figure out from the remaining piece of information you're given, which is that v dot x hat is minus 10. What is that? What in this sea of characters, what does that mean is minus 10? The first one, right? Exactly. It means that v cosine, it means that this is minus 10, right? Because v dot x hat is equal to the x component of v, which is minus 10. But by the way, that's also equal to v cosine alpha.
This video, is it going to be on YouTube like today?
As soon as as soon as I can.
Okay.
Yeah. Lord willing, the creek don't rise, all that stuff, you know. Children don't break my computer. Internet works, you know, the usual stuff.
I'm not asking how to find it really, but what are you looking for in problem 3 part G, where you write vector A equals v1 vector, v2 vector?
So in part G of problem 3, I said write A equals V1 plus V2, where
Are we trying to find v1, v2? Is that the goal?
Oops, V2 is perpendicular to V. Yeah, you're trying to find a V1 and a V2 which fit the characterization I give right there. Projection, orthogonal projection. Sorry, I may have said something about projections. I don't know. That's what this tool is designed for, right? Like we used it earlier to find the closest point to the line. This is essentially the same question. All right, well, have a good weekend. See you guys later.